I saved $2,008 using statistics. That's pretty cool. When I was in graduate school, my car died. Clutch went out. And so it was time to buy a new vehicle. And being the stat savvy fellow that I was, I decided I was going to go online to cars.com or whatever and scrape their data and use that to build a statistical model, because that's what one does. So I gathered a data set of 467 minivans because I was looking for a minivan because I had a bunch of kids. Well, I still have those kids. They're just not kid-like as much as they used to be. And the problem is that the prices were all over the place. From as cheap to $1,900 to $25,000. And you got to remember, I was a graduate student at the time. I was poor. What I wanted to know is, what is the best deal I can get? Or another way to think about it is, what is the car that was cheapest given the features that it had? Because I didn't want to walk away with a 30-year-old car that had 600,000 miles on it. I wanted something that could be reliable, that I could use for many years, that didn't break the bank. So how do you go about doing that? You have a data set, what do you do? Well, there's traditionally two different stats mindsets that people have. There's the testing mindset, which is how most students are trained. The entire focus of a lot of stats courses is, which test do I use? Is it a one-way ANOVA? Is it ANOVA? Is it a one sample t-test, two sample t-test, related t-test, factorial ANOVA, and ANCOVA? But none of that would help me in this situation. That is not going to help me figure out whether I'm getting a good deal or not, because this testing approach really just asks whether there is a difference from zero. That has nothing to do with the question that I'm asking. And more often than not, it pigeonholes people's research questions. The better way to think about it is from a modeling approach, which is what I did. So in order to use statistics in a practical way, you have to be able to translate your question into something that can be answered with statistics. So again, what did I want? I wanted a good deal. Well, what does a good deal look like? Good deal is cheaper than what you would expect. Well, now we should probably define what it means to say, what is expected? So then the question isn't, which test do I use? The question becomes, what analysis can I do that will tell me what the expected price is? And then once I know the expected price, how do I then figure out whether a car is underpriced? Do you see how that translation happened? So again, I start out by asking what I want to know and then trying to figure out a way to use statistical modeling to do that. So for the expected, we could just run a simple regression model where we predict the price of the car from the mileage, the year, the make, the model, type of engine, transmission, drivetrain, and maybe an interaction effect between mileage and age. And then to figure out what the expected price is given those variables, we could do this. Predict model. Very easy. If you do that, it'll tell you the predicted price of every single vehicle in the data set. But again, I want to know, what is a good deal? How do you define a good deal? It's cheaper than expected. Or, in statistical terminology, we would call that a residual, which looks like this. And here's a scatter plot showing the relationship between a couple of variables and the outcome. And again, I'm looking for situations like this, where we have really large negative residuals. So the key insight from that analysis was that the deal quality was defined as the residual. So what did I do? I sorted the data set by those that had the largest negative residual. And then I saw, okay, there were cars in there that had 200,000 miles on it, or that were built in the 1700s or whatever. So I said, okay, I want a car that is not more than 10 years old, and I want the car to have less than 120,000 miles. And with my newly sorted data set that looked like this, I identified the lowest three residuals. And then I went to the dealerships to look at these three cars. And yeah, they were cheap for a reason. Like, one of them was missing its engine. One of them looked like it had been used as a punching bag for the Incredible Hulk. And I think the other one, they had accidentally forgot to put in a 0 or something like that. So, that was unfortunate. The end. Just kidding. Not the end. Although I was a little disheartened that my first approach didn't work, I decided on a new strategy. What I decided to do was I went to the nearest dealership to my house, and I perused their inventory and found a car that met my criteria. It had like 92,000 miles. It was like 5 years old. And it had those really nice fold-down seats. I just loved those. Because that meant I could put a sheet of plywood in the back of my van, which was just awesome. Total game changer for my budding woodworking hobby. And I looked at the price tag, and the dealer had actually priced it just about where the model predicted it should be. So then I entered the characteristics of the car. I put in the year, the miles, make, model, drivetrain, all that sort of stuff. And then I asked my model to predict the price. And guess what? The predicted price ended up being basically what the dealership was offering it for. However, my statistical model also taught me what a good deal was. So I looked at the size of the residuals for the 3 lowest cars and decided I was going to offer a price that was about the same size as those residuals, which ended up being like $3,000 less. And after some haggling, I ended up walking away with a car that was $2,008 less than the asking price. So I saved $2,008 with my statistical model because I wasn't guessing anymore. And sure, you could use a Kelley Blue Book value, but what's the point of getting a PhD if you can't use it to buy less expensive cars? But here's the bigger lesson. I'll tell you what didn't happen. I didn't perform a t-test. I didn't compute a p-value. I didn't even ask about statistical significance. Instead, what I did was I defined the question that I wanted answered, which was, what car is a good deal given the features? And I translated that into a quantity that I could estimate from my statistical model, and then I used the model to compute the quantity that I wanted. And here's something that it's taken me a long time to understand. Statistical tools don't answer questions. You answer questions. And you ask questions. What the statistical tools do is they create quantities that you have to decide whether they answer the question that you're actually asking or not. Because too often what people do with statistics is they don't use it to answer questions. Instead, they use it, as Tukey would say, for sanctification or for justification. They use statistical models to justify their conclusions or to sanctify their conclusions. Basically, it's people's attempt to say, hey, it's not my analysis, that's what the data say. The data supports my hypothesis. Or another way to put it is that the data becomes subservient to the researcher's wishes in such a nefarious way that it creates the illusion among the person using statistics that it's actually the statistics that are sanctifying and justifying their results, when they're not. Because what is data analysis about? It's about analyzing data. Who'd have thought? And it turns out our data really want to speak to us. There's so much richness in our data. There's so much information it can give us. But if we're too pigeonholed into this idea that we need to do some sort of test to sanctify our hypothesis, then you've missed the point entirely. Instead, what we do is we ask, what do I care about? What do I need to know? Is there some way to turn what I need to know into a number? And if so, what tool will give me that number? Because honestly, this isn't about cars. I do this all the time. You might call it statistical thinking. I've used the same approach to figure out which house meets most of my preferences the best. I've used it to try to figure out what's the best way to spend my credit card rewards. And I've used it to figure out which health insurance plan is the best for my needs. And one thing that I've learned is that this is something that is intuitive to me. I had a professor when I was in graduate school. I don't remember how the conversation came up, but he just said, you want to know what my biggest weakness as a teacher is? He said, I don't remember not knowing this stuff. It is so intuitive to me that I have a hard time empathizing with people who don't get it. And I don't feel like that about statistics in general. I remember being totally overwhelmed and confused by it. But one thing I don't remember struggling with is being able to translate the questions that I have about my data into numbers that a statistical model can actually answer for me. So I admit that's kind of a weakness of mine. And in some ways, this video has been an attempt to explicate. That's a word, right? Explicate? Yeah, it looks like that's a word. And I think that word actually makes sense in this context. So this has been my first attempt to explicate how that process happens for me. And I think that over the next couple of videos, if you guys are interested, I might run through more examples where I use this sort of approach to translate questions that I have into quantities that statistical models can answer. So I hope you will join me. And I also hope you will join me in a simplistics class. Have you been yet? If not, you are missing out on the time of your life. It is the who's who of education. You know, like, I'm not going to, like, for privacy purposes, I cannot exactly say what sort of really famous people have taken classes from me. Let's just say it's the place to be. And I've got a live class coming up in May. Mondays in May. So I hope to see you there. And if that doesn't work for your schedule, then please take a on-demand class where you can ask questions of me and I will answer them through a Canvas website. And that's actually kind of cool. So anyway, until next time, peace out.